Okay, good evening, good afternoon. It's a pretty warm day outside today. It's going to get cold out and be kind of not so great one of these nights, though, but I'll take it. We've got just three of us tonight because Lantu has a car breakdown right now, and she's just not going to make it. She's focusing on just getting off the highway and getting somewhere with her car. So hopefully we can get a good recording. So what I want to do is get back onto the Z transform. I've been grading the homeworks. I have approximately halfway through, and I made some observations. So I decided I wanted to start off, since we're going to be doing more and more of this all the time, where we have to bring in time domain, frequency domain, and now Z domain, sampling theory. I mean, it's just going to keep building and building. So one of the things I want to go just take a look at on one of the problems from set number 2 that I haven't graded everybody's paper, but I've certainly seen two people kind of miss the boat, not getting the wrong answers at all, but just taking what I think is not the right approach. So in this problem, you were given an h of e to the j omega frequency response for some system, and you were to find the impulse response, and then you were to take the frequency response and write it as I'm just rereading what I have written down here. Find the LCCDE from the frequency response. Then in part C it said, and this is the part of the problem that I'm interested in just commenting on. It said you're given an input that's composed of a constant plus 2 cosine omega naught n. So when you see that n from minus to plus infinity, you think steady state. So you think, okay, frequency response is going to be helpful here. That's what I was hoping everybody would just see, and I thought I put that in the hints. I don't remember what I wrote into the hints, but when it says, for what value of omega naught will the output be just a constant A and not any other component? So you see two components going in, a DC component and a sinusoidal component. So it must be that this system has a characteristic in its frequency response that has nulls in it, which means the gain at some frequencies is identically 0, which means it's going to wipe things out. So what I was hoping everybody would do is they would say, okay, first off, we have to see what frequencies do that. So your detective mind is supposed to say, let me plot the frequency response and just see what's going on. Here I plotted it from minus pi to plus pi. It would have been adequate for a real impulse response, a real system, to plot just from 0 to pi or 0 to 1/2 in the normalized digital frequency, but I see an exact 0 at some frequency. Not immediately clear what that frequency is, but we can go analyze a little bit further, and when we look at what's going on with our frequency response, to me, you focus on the numerator and say the denominator is not going to go to infinity because there's no poles in the system that will cause it to blow up immediately. But we do have, I guess we can go over here and see what it's doing. It's actually nice and stable. It starts at a DC value, gain of 10, drops down, and then it hits 0, and then it comes back up a little bit. But the 0 in the frequency response can be found by setting 1 plus j2 e to the minus j2 omega equal to 0, and that happens, of course, when this e to the minus j2 pi over 2 is equal to j something or another. So it's going to be 1 minus 1, and it's going to be equal to 0. So that lets you find the frequency. That's pi over 2, and that is this point right here. So it's 0.25 on the normalized frequency axis. And then the second means of doing things in the frequency domain is to say, okay, what is the frequency response at DC? And for me, I would much have preferred you, and I'll see what the other half has done here, to look at the frequency response and say, put in omega equals 0, and I'm going to get the DC gain of the system, right? That's kind of like what you would do in circuits. You would say, what's the DC gain of the system? I'll put in omega equals 0, and I do that in the second part over here, e to the j0, and I find out I get 1 plus 1 and 1 minus 0.8, so I get a gain of 10. And that's without actually drawing the picture. I can just get that, and then I know to get 40, I just need to set A equal to, well, I set A equal to 40 in order to get the desired 4 coming out of this, the constant A, I mean, is what I'm going to get. So A is going to be equal to 40 in this case. Not a really big grinding thing, but I'm just saying I would rather have you look at the frequency response. This problem was set up that way on purpose. It was like you're going along in the time domain, and it's like, when do I switch? When is it appropriate to switch to the frequency domain to get the most bang for your buck? And that's what this was. I could very easily throw that on the first exam, too. I mean, I've done it before, just because I think you have to keep your mind kind of focused on the idea of making life easy for yourself. Don't approach something and try to make it more complicated and use the skills. If you're working an exam problem, of course, it's different because you don't have the computer. But if you have the computer available, you can do a sweep very, very easily using FreakZ. So I think that was really all I was after with that. I'll try to give some hints for the homework that's running out here right now, though. There's some problems that are very nice and easy, some problems that are moderate, and then there's some problems that are really going to make you think. The last problem seems like it should be really easy, but it's all rankled up into some interesting understandings. Remember last week we were talking about the region of convergence. We were talking about whether it's a right-sided or left-sided sequence. There's some real subtle things that last problem has in it, which require you to just sit still and pay attention and figure it out. So I'll probably go take a look at that one. I may have to open up my tablet and look at the problem statement since I don't have a book with me. So last week we got up to the inverse Z transform, and I mentioned briefly we're going to do the lookup table method with the inverse transform table. However, the origins of that method are really in the complex variable theory, saying you can do contour integration if you wanted to. The inspection method is kind of silly, but the inspection method just says, if it's that simple, you can just look at it and see what it is. You know, examples of the inspection method would be like these first 3 transforms. Pretty obvious from those, and then extensions of those perhaps. The others are a little bit more complicated. So when you have a composite, a ratio of polynomials in numerator and denominator, then you have to go after the partial fraction technique to break it down into terms. And we'll start with a generic numerator over denominator where the order in the numerator is m and the order in the denominator is n. And if we write that in positive powers of z, which is what I'm doing here, we'd see that how we proceed depends upon whether the numerator order is, what the numerator order is relative to the denominator. If m is greater than n, there will be m minus n poles, and if n is greater than m, then there'll be n minus m zeros at z is equal to 0. In all cases, though, this is true. See if my pen is working. Wait a minute. Yeah, I wanted to go for that one. Number of poles always equals the number of zeros. And what you have to think about with this rule, and I can think of Dr. Trimboli probably talks about this in 3205. The fact that the number of poles equals the number of zeros. Does he talk about that?
Yeah.
And what makes this mysterious? The pole or zero could be at infinity, and that way, if you're looking at a sheet of paper that describes the poles and zeros, and if they don't add up to be equal, then you have to think, okay, there must be a pole or a zero out at infinity. So you just have to keep that in mind and not lose sight of that. The other thing is the second bullet there that I circled, just saying we can do partial fraction expansion if the function is a proper rational function, which means, first off, the leading coefficient on the denominator is not 0, and that the order of the numerator is at least one less than the denominator. If it's not proper rational, it's called improper rational, and the way we get to the expansion for that is to divide denominator into numerator to reduce the order of the denominator or numerator by 1 at least. I mean, get it to be m less than n. So you divide as many times as necessary. The examples I'll go through don't require anything more than one division, but I think that's one of the things that you've probably gotten weak on since we've had calculators and everything, and that is doing long division. True? Did you like doing it in K through 12? Did you have to do it though? Good. I mean, if they get rid of that, we're going to be in trouble in engineering. We're going to have to say you have to learn how to do this then. But doing it for, a number divided into another number is one thing. Doing it for a whole expression or a polynomial is a little bit more tedious. So we'll do that for at least one example here. So that proper rational is necessary, and then we start with the concept of distinct poles and then build up to a solution for repeated poles. So for distinct poles, we're thinking that we can do an expansion of y of z into a sum of first degree poles where we have dk as the non-zero poles of x of z. We're not worrying about poles at 0, we're just worrying about poles that are not at 0. And then we're doing our expansion with respect to those non-zero poles. Now this is a really super big deal, but I don't know if I want to make it a super brilliant color. This is what I warned you about last week. I said we're always going to expand using negative powers of z. But in many texts that I've bumped into, they might use positive powers of z. I don't know what you did for, say, 3205. I honestly don't know. Originally, they were using a book that was developed by at least somebody from Georgia Tech, which meant they were connected with this book. So they always use negative powers of z. But if they switched, it could be confusing. If I was teaching that other class, I would say, no, I don't want to do that because it's going to cause problems. If you get a Shams Outline series or one of those math handbook types of things, which I highly recommend actually, I have one of those at home, the Shams Mathematical Handbook. It's a paper book. I realize the internet can do everything and anything, right? But sometimes you just like to open up a paper book and look at something that you can hold on to and touch. I have one of those at home. I refer to it periodically still to this day just because I've learned how to get my way around on that book fairly well. Okay, so we want to look at tables that do negative powers of z, and that's, this one is sufficient for everything that we're doing in here. So there it is. That's on the cheat sheet that you'll have for exam 1. So the expansion is very simply this. It says the coefficient ak is just multiplying x of z, a proper rational function, times the pole term whose coefficient you want to solve for. So up here, we're just going to go after the particular ak and then that's the term we're going to multiply x of z by, and that conveniently annihilates the pole that would be blowing up if we substitute in z is equal to d sub k. So we're canceling that off, and then we're sifting out the so-called residue. And this, I call it the residue because it's what happens when you're doing the complex variable theory. It's the exact same thing. Terminology is similar. We're using that to get our partial fraction coefficient. And another little tidbit in here is I recommend when you're doing these substitutions, you plug in the inverse of the pole, so that way you've got what you need to replace e to the minus 1 by everywhere. Otherwise, you get into this, do I flip it or don't I flip it? I just start writing it down as the correct number to plug in, and that's 1 over the factor. And we'll see that in the example. So in general, then, we can do all the non-repeated poles in this fashion, and then the long division is what's out in front here. That's done first off. If we have multiple ordered poles, so if some pole has a multiplicity s, in other words, it's repeated s times, and it's at location z is equal to d sub I, then we have to expand the above formula to add this other term at the end. So we have to add this stuff. Those are for all the repeated roots. And this is a nasty formula, just plain nasty, I think. And I'm going to show you in one of the homework problems how you can get around it, and I'll show that in one of the example problems too. What makes it nasty is not writing this part down. What makes it nasty is this formula down below here. The factorials and the differentiation that you have to do is what's kind of nasty stuff. I don't know. It's polynomials, so you can say I can differentiate polynomials all day long and I never have a problem. But when they get all wound around themselves, it starts to get messy. But formally, that's how this is done. So if we have more than one repeated root, then we'll have more than one of these terms. So the number of terms that I put the bracket underneath is just for one repeated root, but if you had multiple repeated roots, then you'd have to add multiple versions of this term for each of those repeated roots. We're not going to specialize in that. We just don't need to do that. And as a matter of fact, I love this math. The fact that it exists is exciting, but the fact that it's hard to make your way through it is also believable, right? Having a nice equation, I'm just thinking of electromagnetics, for example. You can have nice equations for the field at a point of some weird geometry, and then you have to integrate to get there, and then the practicality kind of goes down the drain. So in electromagnetics, especially, they're interested in numerical solutions. We don't have to go to that extreme by any means, but we have tools, and Python has a nice function called residue z that you can use to get all of the coefficients. It gets it to within numerical precision, and it's also subject to some, case where the finite precision, floating point numbers, or double precision numbers possibly could lead to some instability in the calculation routine, so it might possibly get values that don't make sense. I don't know, does that bother anybody? I mean, one of the things I had to do in my early days of teaching, I was using C and then C++ and then MATLAB and then Python. I had to write routines to handle calculations where there were things that would go unstable in the math. And then you have to learn how to write code where you patch something up it has a singularity at a certain point. You have to do something to make sure it gives you a nice answer. And when you're writing like C code or C++, you get better at this, and you learn a lot of respect for it too. You have to understand, why is it failing at this point? So we already learned in the first examples of the Z transform how we would inverse Z transform. So we know how to go back over to here if the ROC for this particular term is magnitude of dk greater than, or magnitude of dk is less than, say that right, region of convergence for this term is right-sided, so it's the magnitude of Z. Let me just write it in here. You know, we have that, and then we also learned if we had the left-sided, it's the interior, so we know how to do that stuff. There are problems floating around in all of this assignment where we have these scenarios, both right and left-sided. So let's take first example. This one is in the book, I believe. It just says, let's find the sequence x of n. It could be, if this was h of z, it could be finding the impulse response. But first thing we have to do is say, is this proper rational? And when you're studying it, you don't have to convert to positive powers of z unless you want to. You just have to look at it and say, what's the largest negative power of z in the numerator? It's 2. In the denominator, it's 2. So the numerator is not 1 less than the denominator. So you have to do line division. And then generally, there'll be something like this. The region of convergence will be specified, or the region of convergence could be given as the waveform as causal or anti-causal, and those types of terminologies show up a lot of times in the book problems too. So if it was causal, you would just say that the region of convergence is the exterior of the circle corresponding to the largest pole radius, right? And then, like last time, if it was anti-causal, it would be less than the magnitude of the smallest pole radius. So this one just picks this scenario, magnitude of z greater than 1. What does this also tell you, just as a side note? If you're given the ROC as magnitude greater than 1, we know it's going to be causal, right? Because you can go all the way out to infinity with it. It starts at 1. What does this tell you about the roots or the poles in x of z? Just without knowing the absolute numbers, but we know what? Correct. Does that make sense? Because that is setting a boundary on the region of convergence. So there must be at least one of the roots of that denominator is at 1 or minus 1 or j1 or minus j1 or something like that. We'll get to that in a second. Right now, though, we just do our line division. So we divide the denominator into the numerator, and the whole objective of the line division is to be able to reduce that z to the minus 2 down to a z to the minus 1. So you look at the line division, you say, how do I proceed? Well, you want to be able to get that annihilation in there, right? Because that will reduce the order down for us. So we multiply by 2, and then our remainder is 5z to the minus 1 minus 1. So we're done. Long division gives us a constant of 2, and then we get this proper rational function left over. And now we just have to find the roots of that denominator. So I cheated a little bit. I said, let me just try 1 minus e to the minus 1, and what does that give me? If you don't want to be like that, you can go to the quadratic formula, right? You could go to Python, roots function, or something like that. Most of the time, though, you can finagle it if you've got some information. If you're desperate, though, you should always be careful. I mean, on an exam, you got to just work fast. If you have a calculator that can root polynomials, great. In this case, I just looked at it and I said, how about it's 1 minus e to the minus 1? Can I see how I'm going to get minus 3 halves? And I can see immediately I'm going to get minus 1 half, and I'm going to get minus 1 from the 1 times minus e to the minus 1, so that's 3 halves. I'm not going to dwell on that. I'm going to let you just fiddle with that, make sure you know how to do it. But you could do that, and maybe I should just say our coefficients are 1, minus 3 halves, and 1 half. So if you're wanting to go for a quickie check, you could go over here to Python. What is it, minus 3 halves? Oops, forgot that. Put a bracket there. Okay, so the roots are at 1 and 1 half, which is what we have over here. In other words, what power of z will make this term go to 0? That's going to be z to the minus 1 equals 2, and what value of z to the minus 1 makes this go to 0? That's going to be z to the minus 1 equals 1, which is 1 over 1. Good. You can see how you can make mistakes, though. If you just start making your brain crank too fast, you're going to invert too many times, and then you'll get the wrong answer, right? So I always make sure that's going to happen. When you do the coefficients, it'll kind of resolve some of it. So we have to solve for A1 and A2. So we take our original proper rational function that we were left with over here and multiply it times the pole whose residue we want to solve for. So we're going to multiply this thing in the red box times 1 minus 1 half z to the minus 1, and that will give us as the leftover 1 minus e to the minus 1. And that particular pole is at 1 half, so we plug in z to the minus 1 equals 2 in place of z to the minus 1, and then the math is more bulletproof in my mind. Minus 1, 2 times 5 is 10, 1 minus 2, minus 9. Do the same thing for the second residue and get 8. And then put it back together, and there it is. We just have to inverse transform term by term. And because of the fact that the region of convergence is the exterior of a circle, in this case radius 1, we know both sequences are right-sided, right? There's no 1 left, 1 right, 2 left. They're both right-sided. And by the way, most of the time in exams, I don't have two-sided sequences. I don't have mixtures and things like that. The possibility exists, but most of the problems that I usually give are not all wrangled up like that. Homework, totally different story. The homework problems tend to thrive on that. I think the authors of the book just wanted to give problems that really test your robustness for doing the math part of it. So now we can use our formulas up here for the right-sided. It'll be this. To take our partial fraction expansion terms and take them back to time domain sequences, coefficient AK times the pole raised to the nth power times U of n, and do that twice. So down below here, we get the inverse Z transform of constant 2 is just 2 delta of n, and then minus 9 times 1/2 to the n, and then plus 8 times 1 to the n, which is just 1 times U of n. So pretty much a done deal there. We could have modified the problem to have the ROC be magnitude less than 1, in which case then we'd have two left-sided sequences. We could have said it was a mixture between 1/2 and 1, and then we would have had the 1/2 term, 1/2 to the n term is still hanging out as U of n, and the 1 to the n, no, I got that backwards. Yeah, and then this term right here, the pole at 1, it would be left-sided. So we're going to get a minus sign in front of it, and then U of minus n minus 1. And that's just, again, the lookup table from what I wrote down here. Or if you want to go back and just get used to the idea of looking at this table, you can just read it off of here, because most of the entries in this table are managing both directions. The right-sided, the left-sided, the right-sided, the left-sided, for a bunch of them, or at least the first few, and they're the most common ones. I forgot, I was at hand therapy just before this, and she said, you should be able to do this. So I've been going without it, because I get massaging and I do my exercises with my hand. So I'm better. I'm in a dangerous position. If you wanted to come and tackle me, you could really make me get into pain in a hurry. But what's that?
I stick miles on you.
Okay. That's making me think back. My son and someone he works with at my church came over to watch the Bronco game last night, and they were watching this guy on YouTube, this medical person. Does any of you follow this? There's somebody on YouTube, a medical doctor, that when there's an injury in either a baseball game or football game, they instantly post it.
Yeah,
Have you've heard of it?
Yeah, I've heard of it.
Well, there was another game. What's that?
You know who Tyreek Hill is?
No.
He definitely broke something in his foot.
Well, is he the guy from last night?
Yeah.
Well,
was it on the Broncos game, or was it?
No, it was another team.
Yeah. Yeah, it was the guy.
It was a guy that dislocated his knee, right?
Yeah. Well, and somehow like his foot was like turned like the opposite way. So I thought it was his leg at first, like he broke his tibia or something, but I guess he like tore many things in his knee. So.
It sounds awful, but to me it sounds amazing that this doctor follows this stuff and does these videos immediately.
Yeah.
I thought it was pretty cool. My son is a, YouTube maniac person. He follows, he'll look stuff up immediately. And you guys probably do that too. I'm not quite fanatical like that, but I do use YouTube. If I'm getting ready for a performance or learning some music or something, I'll find things on YouTube where another ensemble has recorded the exact same arrangement that I'm trying to learn. So it's nice to listen and hear stuff. At any rate, getting tackled made me think about how dangerous football is. Okay, so we made it down through that part. Now we're going to go to the next example, and our next example is a repeated pole. So we have, you got a question?
Why does the numerator need to have a lower power than the denominator?
I don't have an example written out, but if we were, okay, and maybe I should work on this during the break time or something. If we were to take this problem right here and just merrily went away and said, okay, maybe I'll get the answer just thinking about this. And then, yeah, I have the answer already, actually. And then you would solve for the residues, A1 and A2, by multiplying the original x of z by 1 minus 1/2 z to the minus 1 to get A1, and so on. You'll get an A1 and A2, but if you were to try to put this over, take this answer from here, in other words, once you get A1 and A2 and try to go back to the original x of z, look what's going to happen. You're going to get A1 times 1 minus z to the minus 1, and you're going to get A2 times 1 minus 1/2. Then you're going to have the original denominator. What's missing? You're not going to have that. You're not going to have the z to the minus 1 or z to the minus 2. I mean, you can't synthesize that from this improper rational function. Does everybody see that? If you come back over to here, we've just taken this and cross-multiplied so we can put it over a common denominator. When we put this back together again, we will not be able to get a z to the minus 2 term. Where do I see this when I'm grading papers? I would rarely see this on homework, but I might see it on an exam, just because you do this, you just push forward fast, and you get an answer, and you'll say, oh, here's my answer, but you will miss the long division term. If you're checking this with residue z in Python, though, you will be able to put the brakes on immediately. So does that help?
I think so.
I probably should be able to give a more rigorous answer, but I'm just thinking practicality. It just shows you can't put it back together again. Okay. Okay, now we have a repeated root, so we go right off the bat. We don't have to do any polynomial factoring. We just have to say, again, we have a causal signal because we have the region of convergence is the magnitude of z greater than 1. We also know that we have roots at 1, but in that case, we have a root at minus 1 and a double root at plus 1. This was not multiplied out for us conveniently, so everything is right there in your face. We have A1 over 1 plus z to the minus 1, so that's our simple root, non-repeated, and then we have a double root at z equal to 1. Oops. I don't know what I did. I hit something on this thing. At any rate, we have C1 is the coefficient over the 1 minus z to the minus 1, and we have a C2 over 1 minus z to the minus 1 quantity squared. So this is where we have to go back to this formula, and this is where things get messy. And you do have this on one of the homework problems. So there's an out for this. So first I'll just follow the approach, though, and then I'll show you the alternative that you can do for this particular scenario. So right away we can easily solve for A1, because all we have to do to solve for A1 is we're going to multiply x of z by 1 plus z to the minus 1. That'll make this cancel out. and then we'll be left with 1 over 1 minus e to the minus 1 quantity squared. We plug in the inverse of that root, and that root happens to be at minus 1, so we take 1 over minus 1, we get minus 1, plug that in for z to the minus 1, and we get 1/4 for our coefficient. Now we press on to go for C1 and C2, and again we can get after C1 pretty readily, because again what we can do is we can multiply both sides by, I'm going to flip sides on this now. We can multiply both sides in this, the equation for C1, multiply both sides by (1 minus c to the minus 1 quantity squared). So that will cancel out. And we can effectively immediately get our coefficient of 1/2. I don't think I did that right here. I did not do it that way here, but I know that's what I can get because I can get away with that. I don't have, I can use the same residue formula in this particular case. And the reason why I can do that for C2 is that C2, when we have 2 repeated poles, we don't have to do any differentiation, and we only have 0 factorial, which is 1, and then we just have the denominator here minus 1 to the 0. So we'd have to go back up here to actually understand that, I think, how this formula works, but it is in here. If we're going to solve for m is equal to 2, the derivatives go away, and we're multiplying by that pole to the s power, and then things this pretty much reduces down to the simple pole case for that highest coefficient, the one where s is equal to 2. I'm guessing maybe you can remember stuff like this from circuit theory or somewhere in 3205 where you maybe did this Laplace transform stuff. Similar ideas where you did partial fraction expansions. But now in this particular problem, when you have to come back and get C1, we can't do that because now we have to go with this business out front. We have to have 1 factorial, which is still 1, but we now have to take the derivative of this with respect to w, and w is really just the substitute for z to the minus 1, but now we have to differentiate this. So we have to use the quotient formula from calculus and just jump in it. I'm not jumping in it. I'm staying out of it for right now. I'm just saying that's what you'd have to do, though. You would differentiate 1 over 1 plus w with respect to w. So you're going to get a little bit of a mess there. Not super bad, but you're still going to have you have to do some calculus, polynomial derivatives. Then substitute in what that root is. That root happens to be 1, so that's an easy substitution. Then you get 1/4 for that. But now I'm going to show you how you can do something more fundamental without having to resort to differentiation of ratios of polynomials. Is that exciting? I'm certain you've done this before, but I'm just going to review it because you're going to probably going to say, I've done that before. I just don't remember. So maybe I'll just ask, what do you think? How could we do this if we didn't want to, if we wanted to be more proactive in reducing the amount of calculus? We know right now that we can use the basic simple residue formula for A1 and C2, because that's the highest order. What we're stuck with is on C1. So the technique that I learned a long time ago in circuits is if I only have to solve for one coefficient, I can just write an equation out to solve for one unknown. So what I do is I take the expression right here and I choose a z to the minus 1 not at a singularity. When I say not at a singularity, it's going to be not at one of the poles. So what do you want to pick? You want to pick it easy too. In this case, what value of z to the minus 1 is good? 0. Agreed? Okay, so we pick 0. So pick z to the minus 1 equals 0. So if I do that, I'm just going to try to write this down below here. I'm going to start by using what we know up above here. So I'm going to get rid of this. So I'm going to take what x of z is, and I'm going to plug in z to the minus 1 is equal to 0. So I'm just going to get 1 over I just have, no, never mind, I don't have that. That's not right. Good. No, it is right. Thought I was getting too carried away. See how easy it is to get carried away and make a mistake? So numerator is 1. The denominator, the first term, is 1 plus 0, which is 1, times 1 minus 0 squared, which is still 1. So that's on the left-hand side. Then over here I get A1, which I already know, and I get C1, and I get C2. So from that, I can find C1 as being equal to 1 minus A1 minus C2. I didn't have to set that up for a fraction, but I could. I'm just going to divide by 1, because there's no constant times C1 in this case. It's just 1. So I can solve for that. So 1 minus A1 minus C2, which in this case would be 1 minus 1/4 minus 1/2, which is going to be 1 minus 3/4 So I get the same answer. Does this remind you of something in circuits, or just something from somewhere? I don't know if there's a name for this or not. All I know, for myself at least, whatever I learned a long time ago didn't go out of my brain. Have you ever been fearful of that in your life? I mean, assuming you're not under pressure. If you're under pressure, almost anything can break. But if you can be relaxed enough, I think your brain's pretty powerful at recalling stuff. Unless it's a football injury like a concussion or something. I mean, which is what my wife went through a week and a half ago with her tripping and falling on concrete. They were very worried about a possibility of a concussion. And I guess now in football they try to get rid of that too. I was watching the Packer game on Sunday. Being that I grew up close to Green Bay, I still like to know if the Packers can play and win at football. I saw that there's these like soft, cushy things that go over helmets. Is there a name for that?
Yeah, there is, but I don't know what the name is.
But it's something that a player can,
Something,
a crown.
or something like that. I don't
Okay.
know.
It looks kind of goofy, but you know, it's like if your employer has to protect your health, they probably have to offer that to anybody that wants one. Just like you might be in an environment where you might, as an engineer, might work somewhere where you have to have something for safety. I mean, I don't think I told you the story about the first project I worked on at Motorola Government Electronics. It was laser communications. It was designed to be up in space, but it tested down at White Sands Missile Range, and they first shot the laser. This is not a high-powered destructive laser. This is communications laser. They shot the laser over the desert floor and did experiments there. I was on the receiver front end for the project, and a company that became part of Lockheed Martin was McDonnell Douglas Astronautics. I think they built some of the first space capsules, actually, but they were out of St. Louis. They were the prime contractor. So then the system flew with an aircraft transmitting down to a dome that was tracking what was going on. And for tracking, they used a beacon laser, and the beacon laser was a very high-power infrared laser system. And in the receiving station inside a dome on the desert floor, there was an optics table that took the output from the telescope that was tracking around the aircraft and did some processing on it. Processing, I mean some light beam processing on it on this optics table. And infrared is sitting there. What's wrong with that? What's dangerous about that? You can't see it, right? It's infrared. So whenever that system was on, like a backup light horn was beeping, beep, 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 and then there was a red siren light in the lab that was flashing, and then there was a bunch of goggles sitting there, safety, infrared blocking lenses. So you had to put those on if there was going to be a test underway, which I later read about what it's like to get your eyeball fried by high-power laser. It's not a pleasant thing to even think about, and it will happen. It'll happen just like that, I think, is what I've read. So eye safety was pretty important, and I was thankful that they provided that, and we weren't allowed. I think we probably got instructed on that the moment I walked inside the facility. At any rate, we've done the inversion. We've gotten the coefficients. Now what we have left is we have the challenge. How do we get this? Here's the answer, and I'm just going to tell you right now. We'll prove this momentarily or a little bit later tonight when we're looking at some of the theorems. This is just what we have for a double pole. We get something that's reminiscent of the S domain. In the S domain, you would get something like T e to the minus AT if you had a repeated pole. Does that bring back a memory? If you had a double pole, you would get T e to the minus AT. So what are we getting here? We're getting a discrete time version of that. We're getting n plus 1, which is like our T, and we're getting a to the n, just like we would have had already. So that I think is memorable. What is weird about this, and this I'll try to explain later, is why is this simply not n times a to the n if it's supposed to be the equivalent of t times e to the minus at from continuous time, and we'll see why that is. To me, it's weird, but it's the way the math works out. And this formula is in the table up above, as a matter of fact. I gave you even more than what you needed up here in this table. I guess I did not. I just gave you the minimum. It's right in here. So you plug in k is equal to 2. This factorial is going to drop down, and then this is going to collapse down to n plus 1. So there you have it, but I'm going to prove this a little bit later, see how that works out when we have a theorem to help. So the last example that I've got here, and there's, by the way, there's the answer. I think that, yeah, there's the answer. The last problem is, what about if we have complex conjugate pole pairs? This is kind of a thing that you learn about with the Laplace transform. I'm not going to spend as much time thinking about it here, but just know that it does exist and it will be dealt with, and this example deals with that. It says, what happens if we happen to have a term of this type where we have complex conjugate poles, and then this is in proper rational form? So what is the expansion of this just isolated proper rational complex conjugate pole pair? Well, we can go, and right off the bat, we can say, okay, we can go back to our standard non-repeated poles formula. We have a distinct pole at dk, we have a distinct pole at dk conjugate. So those are not in the same location, and we can solve out for those coefficients right here using the residue formula. And when you get done, you observe that conjugate of AK is the coefficient for the A sub KK term. That should be kind of like, oh, that makes sense to me. So now what you can do is you can combine that together, assuming that we have a causal type system, so the ROC is going to be greater than the magnitude of the dk complex conjugate poles. We can write this out using our simple residue formula to put it back into the time domain, and then we can do some fancy footwork with exponentials, and we can consider the fact that the dk's are complex and they're going to have a magnitude and an angle associated with them, and the AK is complex, it's going to have a magnitude and angle associated with it. So we can write it up in this kind of form where we have these definitions down below here. This is magnitude and angle of the AK, magnitude and angle of the dk, and this is kind of like the punchline right here. It's going to be an exponentially damped cosine. So it's got a frequency beta k, which is the angle associated with the residue, and that kind of makes sense. The angle of the pole with respect to the unit circle controls the frequency of oscillation. We'll understand that more in a little bit. And then the overall amplitude is governed by the magnitude of AK, the residue, and then it gives a phase shift inside the cosine is the alpha k there. So this is, this is what it corresponds to, and this is in the table. I think to me it's more important not to know the intricate details of how to do this, because I'm not really going to ask you to do this. I don't plan on it at any time, but to be aware of the fact that when you have a conjugate pole pair off in the time domain, this will lead to a damped cosine wave. It has some frequency related to what I just said, the angle the pole makes to the unit circle, and the decaying exponential factor will be controlled by the amplitude AK, as well as RK, the radius of the pole. So if a pole radius is approaching 1, it's obviously never going to decay, and that would make it unstable, right? But if RK is less than 1, then it will decay to 0. So those types of terms show up in the discrete time system. So that's what these bullets are talking about in here. For me, I just take heart in this fact. I mean, and this is an observation you would make if you were debugging something or working with a practical setup where you see some sort of damped sinusoid type of response. You'd say, what's going on in the discrete time domain? It might even be in the analog domain already, but it might have started in the discrete time domain. So you would say, these conditions must exist in the DSP side of things. So I do an example in here just with some numbers in it, carry it through, And this is what it turns into for this particular example. Again, I'm not super excited about saying that you can do this, just knowing that it exists. So whenever you have a complex conjugate pole pair in a system or in a signal, you're going to have this type of behavior in back in the time domain. The final type of Z-transforms is power series expansion. This one is very specialized in how you might use it, but it can be useful in getting at the Z-transform by thinking in terms of a power series expansion. So this is what this is saying. The definition of the Z-transform just says X of Z could be written out simply as this thing on the right-hand side, which is just involving all the terms of the sequence leading to something in the Z domain. And we kind of talked about this last time, where positive powers of Z mean you can't go out to infinity, so those are things from to the left of n is equal to 0, and negative powers of Z means you can't go to 0, and those are to the right. So that had to do with causal and anti-causal. But you can do selected things. Like this just says if this is X of Z, you can just immediately say this must be X of n by just identifying what's going on here. Z to the 2 must be the 1, minus 1/2 Z must be at minus 1, minus 1 must be at 0, and so on. Just be able to see it by inspection and thinking in terms of the power series. If you wanted to go to 1 over 1 minus a z to the minus 1, you could just do a continual division of that, and you would get a series expansion, and then that expansion would be exactly the geometric series that we know converges or sums up to the 1 over 1 minus a z to the minus 1. So that would take us around full circle there. So those are kind of obvious things. The less obvious thing is, suppose you had some transcendental function like natural log. You could do a power series expansion in the natural log, and you could then get at the inverse Z transform term by term for that. This is just an example that's in the book. I've never had to do this myself. I did get exposed a long, long time ago during my PhD comprehensive exam to one faculty member who made me study out of the DSP book homomorphic signal processing, which sounds kind of bizarre, but it had to do with log operations, so that you could take advantage to multiplicative things, and if you take the log of, x times y, you can get the sum. So there were some interesting things from that. And in the earlier generation of the book we're using, that was in that book. And he was interested in that probably from something he had done with research. I've only seen that one time when I had to do a problem for my comprehensive exam from that faculty member. And that was the way my school treated us for the end of our PhD degree. Before we defend our thesis and actually start working on it, we had to pass the comprehensive exam, which was more like a hazing into a fraternity, is what I thought. Every committee member, and there were 5 of them, gave you a problem set to do and to turn in, and then they graded them. And then on an assigned day, you met in a classroom like this, and those 5 people were sitting there with their exams that they had graded, sharing them with each other, like, what did you make him do? What did you make him do? And they were kind of carrying on laughing a little bit. And then the session started with me standing at the board and them taking turns asking me questions to do on the spot. Then to the next guy, then to the next guy. And that was more laughing and more conversing, and it was pretty demoralizing. I did pass, but it was, talk about your brain going blank on simple things. That was kind of what they were trying to do. It was totally about how well do you think on your feet. So They explained that to me later after they humiliated me tremendously. Does that sound like fun? It was okay, though. I mean, we don't do that here, though. We don't do things like that. I don't know why they did that, but that was the tradition of that school. Okay, we're going to take our break pretty soon, but I have this as sort of a nice graphical view of relationships between the time domain and the Z domain. So we have a pole inside the unit circle. We know that if it's causal, if it's inside the unit circle, and this is assuming a real pole, then it's going to be a decaying exponential. If it's on the positive real axis, if it's on the other side, it will be alternating. If it sits up here, it will be a step. If it sits back over here, it will be alternating plus or minus 1. If we take it outside the unit circle, it will now be increasing. And if we take it out on the negative real axis, it will be alternating in sign. Next sort of iteration of that is, suppose we have a repeated pole inside. It will have a bit of an overshoot, and then it will decay down. If it was on the negative side, it will overshoot and then decay down with alternating signs. If we put a double pole right on the unit circle, it will be a ramp, and if it's on the negative side, it will be a expanding plus and minus ramp. If you make it greater, it will be an exponential growing without bounds, and then it will be an alternating exponential growing without bounds if it's on the left side. I don't know if this kind of hits you in any particular way, but to me it goes back to something when I first learned about S-domain things. They would talk about the situation of conditional stability. So a person might say this would be conditionally stable because as long as, if this were a system that had a pole right here, and as long as the driving waveform wasn't going to resonate by putting a pole right at that location, this output would not go unbounded. It would just have a constant value. Whereas down here we see if we come in with a single pole on the unit circle, which would be what the accumulator is, and we hit the accumulator with another step function, we're going to have a double pole and we're going to have a ramp then. And that's analogous to having an op-amp integrator and hitting it with a step function or a bias current, and it will just ramp off to infinity. Or the idea of having a resonant mode like that in a mechanical system too. Obviously, having the poles outside the unit circle for a causal system is never an acceptable situation. The final case in here is if we have complex conjugates. So this is the example we were going through with the conjugate poles and the conjugate coefficients. So this would be two poles inside the unit circle. Inversely transform that, will be decaying. If we're put the pole, I don't know why this doesn't look right to me. Oh, put the poles on the unit circle, it will be an oscillator, and this is a way you can actually make an oscillator in DSP. Put the poles right on the unit circle and conjugates, and you can make something oscillate and not get bigger or not get smaller. And then obviously go unbounded if it's outside. So we'll start here after we take our break. The pictures are just some things for you to think about and just kind of get an intuitive form. I think, for me at least, intuition is very helpful in being an engineering problem solver. If you're a person that just wants to stare at your computer and never talk to anybody, you're probably good. But if you want to be able to, communicate with others and kind of be there to help debug and troubleshoot, intuition can be very helpful. And I guess I would say when you're young and somewhat naive still, you will stick your foot in your mouth, and you probably do want to practice at your computer, like test your idea out with a simulation model or something. Is this really behaving like this? And then once you get more confident, then if you're trying to explain it to others, you can use something practical to talk to them about how things are going. Okay, we're resuming the recording from our break. We were talking about deer hunting and bullets whizzing over your head, so you have an idea that we kind of got a far field here, but at any rate, we're going to look at how we could use Python to check our work, and that's, I brought my iPad up here so I could look at some homework problems later. We can use a function called residue z, which is very powerful in Python. It's a numerical function, so it just gets us to within numerical precision, and this is the help for it, for residue z. So it's going to take a rational function, doesn't have to be proper rational, just give it what you want to give it, and it will do its job. So we'll go back to our first function where we had to do long division, and we have as our and it uses the A and B coefficient terminology we've seen where else. In L filter, you have that B polynomial coefficient set, A coefficient set, and then the third entry is, say, the input for L filter. For freq Z, you start off with B and A, and my function Z-plane works that way. This works that same way. So we have a numerator set of coefficients 1, 2, 1, and our denominator coefficients are 1 minus 3/2 and plus 1/2. And then with this function returns, if you don't take any of the options, just use the default, you're putting in these two coefficients, two arrays. So this is like that's B and A, and then it's going to return 3 arrays. And you have to remember to put in 3 distinct values, otherwise you have to try to disassemble it on your own. And that's just the nature of the way Python works. It forms a tuple that has multiple elements in it, and it might have a matrix of one dimension followed by another matrix followed by another matrix. So you're better off pulling it out as the individual elements, and up here it explains, or actually in words it explains what's going on with this function. So at any rate, R is the residues, what I've been calling the residues. Those are your partial fraction coefficients. P's are the poles associated with the system, and K is the long division coefficient. So in this case, when I look at what R is, I get -9 and 8, and I say, I remember those coefficients from before break, but I don't know which pole they went with again, so I have to remember that. But in this case, you can figure that out because we have P displayed down here. P is going to show 1/2, so that is the residue that goes with the pole at 1/2 is -9, and the residue that goes with the pole at 1 is 8. And then the single long division is 2. So that allows us to assemble this immediately and then write down our answer. Now, I don't want you to work the problems like this. I want you to check the problems like this, okay? This is just a tool that you can use to check things. So second example is the one that had the repeated roots in it. And then, of course, yeah, how did I get, I definitely have to use that. That was last week's lesson, right? The region of convergence is your key to knowing which direction they go in, left or right. So let's take the second example where we have the repeated root at z is equal to 1, and then we have another root at z is equal to -1. So plug that into residue z. And here I do a little trick. I use signal convolve, and I'm being lazy here. So I'm saying in this particular case, I don't want to have to do this multiply out. So you use convolve to do that multiplication. So I actually have 3 first-degree polynomials. I have a polynomial has a coefficient array 1, 1, and that's that guy. And then I have two of those guys here and here. So I'm taking this to the ultimate laziness, letting the computer do all the polynomial multiplication. Remember, convolution is polynomial coefficient multiplication. So I wrap convolve onto itself. So I do the squaring there is the inner convolve, and then the outer convolve is the 1 and 1. And then I can go look at that if I want to. I didn't do that here, but I could look at that if I wanted to. I think I've got that in the sample notebook. At any rate, so plug all of that stuff in, and there's my residues. I've got 1/4. That goes with the pole that's at -1. And then in terms of the repeated poles, it's going to be C1 is what this would be. C1 was 1/4, and that corresponds to a pole at 1 of the first degree. And then the third residue is 0.5, and that has a repeated pole at 1, doubly repeated. And if there was a third degree in here, we'd just have whatever we need to have. You could possibly have a coefficient of 0 stuffed in there somewhere, but it'll carry that all the way through. No long division required, so that contains no information. It just says it's proper rational. Put that back together. Do you want to see any other examples? I mean, you can take this away on your own, I think, and do it. If you wanted to, well, let's just go look at, let's see. I've got this up in here. Let's see if it's still running. It's not running. I've never showed you a single thing on Maxima, and I'm not saying that I want you to get involved with Maxima, but on my tablet here, I'm running Windows Subsystem for Linux. Have any of you ever heard of WSL? You can run a Linux operating system. In this case, I'm running Ubuntu right on top of your Windows 11 machine. Is anybody intrigued by playing with Linux ever?
I tried it.
Okay.
I tried it a few times. Disliked it.
Okay. Well, I have it installed here on Windows, but I have it under Linux as well. So yeah, the terminal is kind of what you have to work with. And it crashed. I was running Maxima, and I have to start it up with a command line. Say use the X11 windowing system. It's more stable, and then launch WX Maxima from the command line terminal, kind of like we're doing for Python. And it comes up here, but I'm not sure. I guess it's readable. So I have an example file that I created called Chapter 3. And what you do with Maxima is very much like what you do in Python. You load packages, and my package of DSP tools that I wrote, that I talked about the first day, is just loaded here after you set a path to it. I set plot sizes. Maxima is similar to the way Mathematica works because they both are symbolic engines. They work with lists. And Python works with lists too. Python calls an array a list, but the lists that we use are called ND arrays, which is a NumPy array, which is a supercharged list in the sense that it acts, vector operations can be done with it. The lists in Maxima are like that. I can do array operations on them, but I'm not necessarily doing anything like that here. So these were some of the things I did earlier. But in terms of Z-transform, you can set up a polynomial, and here I'm setting up the very first example that we just did, where we had a coefficient of 1 plus 2 plus 1, and rather than using z to the minus 1, I'm inserting w in place of z to the minus 1. So here's a ratio of a numerator and denominator polynomial, and I just enter that in with ordinary math notation, and it pops out here. And what you have to do with this, is this too small to see? Because I can make it bigger. And then what I can do here is it has a function called part frac. And part frac takes your expression, symbolic expression, which was defined up here, and then I say I want a partial fraction expanded in terms of W, and it gives me this answer. And you look at that and say, that doesn't look like the coefficients exactly that we had earlier, but then you think about it. If this is e to the minus 1, and I can pull a minus 1 out of this guy, and it'll become a plus 1, and then I'll have 1 minus W down here. And on this term, if I pull out a minus 2, I'll have a minus out here. 2 will go into 18 to give me 9, and then I'll have 1 minus 1/2 W. So I've got what I started with. I've just had to do the long division, or had to do the factoring. And this is I did a substitution here. I attempted to make it work for me by substituting 1 over z in place of W, and it's not particularly fond of wanting to do that. And Mathematica is the same way. In our heads, we can think z to the minus 1 in our partial fraction expansion, all the things we've been running, I have in the notes. But to try to make an algebra computer do that is a little bit less satisfying. And if you were to go to Mathematica, it's the same way. When I say Mathematica, I mean Wolfram Alpha. So here's the second one that we just did, and we had a square in there, and then I say do partial frac on that, and this is the correct answer, but you have to do, again, the factoring, and then the proper coefficients do indeed come out. The reason why this is important is if in the special problem that's got more coefficients, you want to see it get closer to the answer rather than using residue z, you'll get rational numbers out of this. You'll see ratios of integers rather than actual decimal point values, and then it's a little bit more tedious. So I think I still have it running in here. Yeah. So here I took an example in Wolfram Alpha, and it will do a partial fraction expansion on it. And here you use, rather than part frac, it's called a part, and a part means separating this into that, and then you do the factorings on this for this particular example, just like I was doing in Maxima. I'd pull out a minus 3, divide it in there, and get a minus 2, and then I'd have 1 minus 1/3, and so on and so forth. It depends on how you want to approach it for checking your work. Residue z works well. It's just that if you do, when you do it by hand, you're not going to have decimals. You're going to have integers, right? Ratios of integers. So you'll have to just convert it back at the end of the problem. Okay. If this stays alive, and Maxima is a very temperamental program. It likes to crash, especially under WSL. But I do have GNU Radio Companion running on here, which is a software-defined radio application, which I used for the final project last year to capture the AM broadcast band and then map it through a USB driver into GNU Radio running in Linux, and then eventually get the file saved out. And I did that on a different laptop, a Windows laptop though, that I have at home. And if you're into that stuff, which I sort of am as a hobbyist, you can make Windows, which has its USB interface, take its USB devices and become part of WSL through a mapping tool that an open source author wrote, so that you can do things. And I did this and ran Vivado. You were, Lake, you were talking about FPGAs, and I was mentioning Vivado, right? So I have Vivado on this other laptop, and it's installed under WSL, so it's the Linux version, and I can put my FPGA board on my Windows machine, and then I can say reassign this FPGA device to Linux, and it lets me control it and write code to it, and then talk to, I use the analog discovery to look at the outputs from the stuff. Is that better?
Yeah. I think so.
You know what that chair's here for? That's,
It's for the professor.
no, it's not. It's actually for special needs people. Every classroom has to have one of those.
I guess that's it.
I mean, it's yours. I mean, it's just like if you had a disability, like you had to take the exams in the special learning center, you'd be able to say, I don't know how you fight over that chair if two people in a classroom need them. I just know every class has to have one of those. We know all those things because we're supposed to be familiar with all that stuff. So, okay, back over to where we were. Okay, here it is live in Python. So I said I would take a look at this concatenated convolution that I was mentioning, and you used convolve a lot in your first assignment, whereas in that case, it was better to use the one I defined in my package, but here, it's better to use signal.convolve. And see here, I did this concatenated convolve, and there's the coefficients on my third-degree polynomial for this particular problem right there. So you had a question about this?
Run, like, Jupyter Lab on here,
Mm-hmm.
and for some reason it's not giving me, like, the plots. I don't know why, but that's all.
We can talk about it when we're not on the camera or not on the video recording, but that error warning is my problem. I fixed it. I pushed a change up, but it's not going to be in a version that's released. You just have to deal with it. But that's just a warning. It's not stopping you from getting a Z-plane plot, is it? You get a pole zero plot?
I mean, I don't see a pole zero plot, but it's fine.
Well, no, you should. I'll pick an example. If you got a minute after we get done, we'll look at it. So, okay, there's not really much in Python to be using for the Z-transform chapter except for residue Z. That's the main thing, and we have an example coming up here that we'll get to with one-sided Z-transform. So now we're into properties, and linearity holds. No surprise there. What would your life be without linearity? Yeah, it'd be much more complicated. I'm thinking of when you said you're working for analog devices, that was Linear Tech, right? The name of the company that they bought, Linear Technologies, was consumed by analog devices in the building. Yeah, they've consumed actually many companies, but that's what that division was. It's up near Chapel Hills Drive in that area, up from the mall, Chapel Hills Mall.
I'm actually in the location Centennial, which is the old Maxim.
Okay, yeah, that's the other company that Maxim has some nice parts. They had a DSP board that I looked at to evaluate for a while. Okay, linearity, really not much to proving that, except that we ran into this last week. So if you're taking advantage of linearity to do a Z-transform, you just have to make sure that the region of convergence is the intersection. Time shifting, this is a big one. Time shift by n-naught samples, and that becomes, through the factoring of just the definition of the Z-transform, a Z to the minus n-naught. So when we draw block diagrams, which we'll be spending a whole chapter on, flow graphs and things. We put inside the block diagram z to the minus 1, and that just means a one sample delay. I just threw that out there because you see that all the time in block diagrams. You can put anything inside the block diagram, but if you're putting in a z to the minus 1, that just tells you it's z to the minus 1. And if you're doing it, say, an FPGA implementation or something, you would prefer to put in the individual delay blocks rather than z to the minus 10, meaning that you have 10 sample delay. You'd want to be able to count the fact that you've got to have 10 registers to hold it in. Region of convergence, you may add or delete 0 or infinity depending upon what that shifting does, because when you shift, you put in that z to the minus something if it shifts it to the right, and then that's going to exclude 0. If you shift it back to the left, then that's going to put in a positive power of z, and that's going to exclude infinity. So that's one of the kind of cool things to think about with delaying any sequence. You're effectively just multiplying it by z to the minus n naught, and that either moves it in this direction, so it moves it to having all negative powers of z, or if it backs it up, it's going to have mixed positive and negative, or backs it up further, it's going to have all positive. So any expression will have that kind of behavior due to the z to the minus n naught. So let's just take a simple example. We have find the inverse Z transform of this. We look at it and we see, just like in the Fourier case with the e to the minus j omega, we could say we have z to the minus 1 sitting here. So let's just pull that out because that's the delay theorem. So we can just operate on the inverse Z transform of 1 over 1 minus 1/4 z to the minus 1 and apply the delay. Whereas if we don't recognize that, then we're going to have to do long division. Because we see we're in proper rational. So we do the long division, we get the minus 4, we get the 4 over 1 minus 1/4 z to the minus 1. And then you could combine those two terms together if you wanted to, and that's what I did right here. Because I know that with that delta of n, that's going to cancel the first term in the u of n, because you have a minus 4 and we have a minus 4 plus 4, so we end up with effectively 1/4 to the n minus 1 times u of n minus 1, and that would have happened if you would have just recognized the delay theorem from the get-go. See how that saves you a lot of grief. And I guess this brings up another point. Some of the homework problems I've given you have answers in the back of the book, and they might have it in one form or the other. So you might argue and say that this is the answer, or that upper line there with the two terms is the answer. They're both correct. It's just one's a simplified or different version of, just massaging it differently. It's same answer. Just comes out with different number of terms or something. Depends on how your brain is thinking on that. Okay, we have multiplication by an exponential. This is multiplication in the time domain, just like we had multiplication in the frequency domain. Multiplication, when we went to the Fourier domain, we ended up with that convolution theorem. Here we're just going to multiply by z, a z naught, some complex value, and that just gives you an x of z over z naught. So it's a scaling action. It's either a contraction or an expansion, depending upon what that z naught factor is. And because z naught is complex, it can rotate it around one way or the other, depending upon what that angle is. This is just, it exists. Whether or not you make use of it It's probably not one of the most popular transforms, but it's fairly powerful. It's somewhat mind-boggling, though, to think about what it does if you expand or compress, and then if you rotate it at the same time. Differentiation, this is a little bit more practical. It says if you multiply a sequence by n, then we get minus z times the derivative of the original z transform of x of n. And the proof of that is just plugging in to the definition of the z transform and then just seeing what happens if you differentiate both sides. You do get, on the right-hand side, you get that popping out from the differentiation. So that's what proves that theorem. Now this is where I pause and use the differentiation theorem to prove the formula that we had earlier for the inverse Z transform of a repeated root. So we can start from this idea right here and just say, what is this Z transform? So first thing to do is to consider what's inside of that. It's a to the n u of n. So that is that Z transform. And then according to this theorem, it says that I would take minus Z times the derivative of that. And that should be my x of Z corresponding to n a to the n u of n. So when I do that differentiation, inside of there I get a z to the minus 1 over 1 minus a z to the minus 1 quantity squared. Interesting, but now what I want to do is I want to modify this back to what we were doing before the break, and that was we were interested in finding out what is 1 over 1 minus remember we had that transform pair, inverse transform of that. How can we use this to prove that we get that answer right up there? So what do we have to do to get there? So both of those are present on the right-hand side in this example. So if we wanted to try to relate it back up to here, what do we have to do? This is sort of you're staring at this, I'm getting tired. You're probably saying, I'm getting blurry-eyed. I don't even know what we're doing anymore. True? It gets to be hard in the second period. But what I'd like to be able to do is just get rid of these two, and now I could move them over to this side if I understand what the action of these two are. So the A can move to be 1 over A over here, no problem. Agreed? Yeah, it's a constant. Linearity holds it. So this would be a to the n minus 1, right? Because I divided by a. Now what about, so now that's gone. So I took care of that. Z to the minus 1. That would show up in the right-hand side if we had a delay by 1 in the left-hand side, right? So to unwrap that and move it to the left-hand side and say it's gone, we have to replace this by n plus 1. So now we're to the point where we're just about done. We can say we have those are relate through Z transform pair. Now, this is almost what we had in the notes beforehand, but what can we do to what's down below here to simplify it. This starts at n is equal to -1 and goes forward, but notice what happens when n is equal to -1. We have a -1 in there and a +1, so that annihilates. It doesn't exist. So we can rewrite that as simply and what am I missing? Something's missing here.
Were we supposed to put in n+1 exponential to a?
Yeah. Yeah, that's what's missing. Screwed that up. Okay. So after we cancel the second time, on the right-hand side, we had a to the n minus 1, but then we replaced n by n plus 1. So we had n minus 1 in its place. So that's what happened. N plus 1 minus 1 is n. So we have n plus 1 times a to the n u of n is the inverse z transform of the 1 over 1 minus a z to the minus 1 quantity squared. If you believed me before, you'd say good. But the idea here was we're using the theorems to just work a problem and just see how you massage things around to get what you want. By the way, since I've already given you this, you don't have to reprove it again. This is in the table, effectively, because I've already proved it using a theorem. Sequence conjugation is kind of esoteric. Time reversal is important, so this is an interesting property. This is, I have a strange analogy to this with wearing socks and turning your socks inside out, okay? You have to listen to this and see if it makes sense to you. If you reverse a sequence and want to compare it to the unreversed sequence, so if you have x of minus n, that's equivalent to taking x of 1 over z. So you're inverting the z, you're making it 1 over z. So it's like what was on the inside in the z-plane is now outside the unit circle, and what was on the outside of the unit circle is now on the inside. So the region of convergence in particular becomes 1 over the original region of convergence. So this is where the sock idea comes in. Why a sock? You turn your socks inside and out, right? Sometimes you draw them that way, or they get inside and out when you pull them off, whatever the case may be. But if you think of the sock, not totally as a sock, but just the cross-section of the sock. So it's like a circle, so the region of convergence is inside, and then it's not in the region of convergence if it's the outside. So when you reverse a sequence, it's like turning the sock inside and out. So the radius gets bigger, 1 over. It's a little bit weird.
Did you put that in your book?
No. You got to have something weird to remember things by, though, right? So I had a professor, though, for real analysis, advanced calculus. I think I told you this already. He talked to us about his bathtub proofs, bathtub proof number 1, 2, 3, and 4, and so on. He thought of his proofs when he was taking a bath.
That was crazy.
He's a native from Missouri, probably, and when I lived in Missouri to go to school to get my doctorate, I did not quite understand the southern twang and stuff that goes on. For me, growing up near Green Bay, Wisconsin, if I drank a soda pop, it was a pop. It was just P-O-P. It was just pop. Other parts of the country call it soda, right? So what do people in Missouri or maybe some of the other southern states call sody or soda? They say sody, right? And then they say several as several. So he would talk about several sodies, and I was like, that's really, It's definitely a different pronunciation, right? It depends where you grew up, though. I'm from the north, so we tend to be really harsh. We don't really drag anything out. It's kind of got a harsh sound to it. So I had a hard time with that. I joke about it because to him it was just natural. It's just the way he talked because of where he grew up. So Serval and Sodi, to me, go together. But some of you, maybe that's your heritage, so you've heard that growing up already. Okay, so an interesting application of this theorem, though, is if you want to take u of n and run it backwards, we'll have u of minus n, and what happens to the region of convergence. So u of n transforms to 1 over 1 minus z to the minus 1. Region of convergence is the exterior of a circle of radius 1. If we use this theorem and apply it, we'll be replacing z by 1 over z, so that's why this is z, not 1 over z. Put it in terms of negative powers of z, we get z to the minus 1, 1 minus z to the minus 1 on top, and 1 minus z to the minus 1. And region of convergence is this inside-out sock. It's the interior of a circle of radius 1, and of course, that manages doing what? That has as a delay, right? Because ordinarily, if we just did an inverse the z transform with a left-sided step function, it should be minus u of n minus 1. That's what we looked at earlier. So get this to erase itself. There is a minus sign in here, so that's why there's no minus sign over on this side, and then the z to the minus 1 just shifts it back to the right by 1, so it's starting at 0 rather than at minus 1. So it all works out as being consistent. Big theorem, utilize over and over again the rest of the semester. Convolving two sequences is the product of their z transforms. Just like from linearity, though, we again have the intersection of the regions of convergence, but we might have a pole zero cancellation, so it could be larger. Absolutely be on guard for pole zero cancellations in this homework problem set. They happen, and they will alter your life. I mean, they'll alter the region of convergence is what they do, because something will go away. Okay, the proof of this is pretty straightforward, just using the definition of convolution and carrying it on through. So here's a neat example, kind of taking us back to the beginning of the class almost. This is an example that showed up in those supplemental notes where I had a unit step conjunction convolved with an a to the n u of n. So we just multiply those two together, use partial fraction expansion on it, and we get that convolution computed right down here. We have the region of convergence as the exterior for the causal case, circle of radius 1 because of the unit step, and then we have two terms, an inverse E transform. We saw this is the exponential response when we convolve the step function with the a to the n u of n. So this was, remember we saw this earlier. This eventually plateaus, by the way. It doesn't, and it's not going to go unstable necessarily. It just hangs out at a final value. That final value is 1 over 1 minus a, right? Because assuming a, magnitude of a is less than 1, this term goes to 0, and then in steady state it's 1 over 1 minus a. There's an initial value theorem. There's also a final value theorem. We're not really using for anything. When I teach the phase lock loops class and have discrete time phase lock loops, then these theorems are useful, just like they're useful in control systems. Okay, so what remains now is doing not the inverse Z transform using contour integration, but instead jumping to the very end of the chapter, the one-sided Z transform. Remember I told you this is just legacy. I didn't want to rip out all the hard work I put into this quite a few years ago. It'd be like a refresher course on complex variable theory, which, remember, I had during my master's degree, I went to a really small school, Michigan Tech, which is Michigan School of Mines in Upper Michigan, did not have a really big electrical engineering program, and they didn't have a lot of graduate courses taught, so I needed courses to get my master's degree without hanging out for 2 years. I got it done in 1 year and a summer, so I took extra math classes. So now we're going to go to the unilateral Z transform, and then this will wrap up the chapter. I do want to balance against this. We really won't dwell on really at all the rest of the semester, but it's interesting to know that it exists. It's kind of like, why did you learn about the Laplace transform in circuits? Because you wanted to solve initial condition problems. You had a transient response problem, remember, you wanted to have an easy way to get that done. Same thing with the unilateral Z transform. So I'll just tell you that's sort of the punchline at the very end. But there's interesting homework problems. You might have questions on them. So does anybody have any questions, just so I know to balance my time that remains? We've got about 20 minutes left. And I've got my solution sitting right here, and I'm ready to dish out some hints. I'm seeing some faltering going on in set number 2, and I want to make sure that you get prepped properly. I did give you the hints, but I just want to make sure you can stay on top of it and ask questions. You can always use Slack. That's true, but there's a couple of key points I want to bring out that will be helpful, and then you can, I'm going to read between the lines beyond what I wrote into the hints. Right now is what I'll do. I mean, not instantly, but I'm more inclined to just buzz through to the end and kind of give you the punchline at the end. Does somebody have some questions to ask already on the homework?
I'm in the middle of working through it right now, so I don't have any questions.
Okay. Okay. John, do you have any questions?
Not yet.
Okay. Okay. Well, I'm going to offer some stuff, and then we'll jump over and look at your Z-plane plot as everybody is leaving. Does that sound reasonable?
Sounds reasonable.
Okay. I had hoped I might see what this is going to be. This is the next chapter where we'll start next week. This chapter is very long because random processes get included. So in the middle of this, we'll jump back into probability, random variables, and random processes. So this is going to be a throwback from the class that you've had already. We have a use for it, though. We have a very important use for it, and it'll be stressing your brain out a little bit. But I'm going to do it because I think it's important. It's what makes things work. The other thing, though, is seeing that I just threw up chapter 4, we have to make the decision on the exam. So I'll get the assignment turned in next week. Do we have the exam one at this date? Because I'll push out solutions shortly after this date, and we could, in theory, have the exam here. Or, as I've done most times, it ends up being on like the 21st, that time frame. We need to have a vote on it, and Lanto will probably want to know, but I won't rely on the video relaying it. I'll just post it into Slack. Have you any of you thought about it?
Do you guys know when our email?
And Miles, you were gonna find out, are you gonna be traveling again?
That's exactly what I'm looking at.
Okay,
I think I'm better for the 14th.
okay. And you guys say you have an EMAG class on Thursday? That's advanced EMAG, right? Yeah. No, wait a minute, it's just the second half of the book. It's the dynamic fields part? Okay. But she also teaches an intermediate electromagnetic fields class, too. Okay. It's the benevolent dictatorship that rules, but I will do it. Most of the time, people have always gone one beat beyond it, but you guys have a reason for doing it. And if things seem really, if you don't feel comfortable with it, we can always veer off of it next Tuesday if we have to. The solutions are already out there. I can talk about the old exams next Tuesday as well. The project will get posted pretty soon here. I'm thinking about changing a couple of problems up. The first problem is going to stay the same. I'm just starting to scratch around with some ideas of some other things. I'm thinking of pulling an old problem that I've had for too long out and putting in something new. Why do I do crazy things like that? Because I work these problems that I bump into in my work, and I say, wow, this is pretty cool. I mean, I think this is almost like if you could learn about it in this class, you'd be a little bit, you might bump into it just like I did. And everything is usually motivated by something that I bumped into.
What day will the project be due?
Right now, the project due date, since we got the calendar up here, we can go right into November. And this is our Thanksgiving week. What's going to happen on Thanksgiving week, we have a take-home exam. So the take-home exam comes out Thursday, Friday, whatever, but you're working it over this weekend. And the idea used to be that it was due always on the Tuesday before Thanksgiving, because classes would be on 24 and 25, and then break would be in here. And people would travel more likely, usually on Wednesday, to visit family, right? Some of you maybe are traveling already. Our family comes to visit you. So I always had take-home exam would be due on the 25th, so you'd have through the weekend, maybe asking questions. I put up a lot of hints for it initially, and then I'll add to the hints over the weekend as you're working on it. You're working on it on your own without seeking any outside help, but it'd be due on Tuesday, usually like at 5 p.m. or something. Project 1 ideally would be due at the same time, but sometimes I've pushed it off over to the Tuesday the 2nd. It's all coming together though, and it's all at this point in the semester, it's to try to head off everything piling up in the very last week. So getting the project out of your hands lets you get onto the second project, which will be this radio project, which is a much simpler project. The first project is fairly tedious. You'll be using Pi Audio Helper, doing some audio experiments too. And you'll be able to get it. I mean, I'll be pushing you at it all along the way. What's going to happen though after this exam 1 is you're going to have to enter a multitasking mode for this class. You'll be working on a homework assignment, which in some cases will get easier, and then you'll be working on the project at the same time. So you'll have to be multitasking for this class. It happens in almost every class you always take, though. Usually I work in homework and a project at some point, so.
And then the take-home exam, is that open notes and open internet, or just open notes? Or?
it's open notes and open internet in the sense that you're not talking to anybody, you're just doing your own research, but yeah. Whereas the final exam will be open notes, open book, no internet. There will be computer things that you do on exam number 2. You'll do some simulations, and I'll give you what I want you to do. You do a calculation of something, and then you'll simulate it, kind of like a miniature version of a problem, types of things that I frequently do in my work. Give you a chance to get feedback, something you can't do in an in-class exam. And I want you to have that hands-on side of it, where you work both sides of it. Now, it's foiled me in the past. The simulation side, I would think the person would see that their theoretical calculation was wrong, but they make the same mistake sometimes, and they get an agreeing answer. It's like, these two agree. I must have done it right. No, you made a mistake in both of them in a different way. But the idea is to try to, cross-check things. Just like in this assignment, the residue Z is helpful to check things out.
With the exam number 1, do we have any note cards or anything?
Yeah, you do. You have one 2-sided page of notes, which you can be working on at any time. As you're working problems, you might just start writing things down, scribbly-like, and then you might formalize it into something that you can read during the exam. Scribbly notes. You don't want to be squinting at it too badly. In one 2-sided sheet. So I've burned up a bit of time already, but I think I can still get back to this. So we'll talk about the unilateral Z transform. It starts at n is equal to 0, and there's some interesting things about it because it's only a right-sided sequence. Regions of convergence are always the exterior of the maximum pole radius, so that actually simplifies things to some extent. The thing where things deviate is the fact that with the 2-sided transform, we have sequence non-zero values that can be to the left of n is equal to 0. And so like with the delay theorem, for example, we don't get the same answer. And we have some sort of strange behaviors that happen, particularly with the time-shifting property. But what I'd like to do without getting super detailed is just come down to the key results. So if you want to get the one-sided Z transform of a sequence, say when you have an n-naught shift, which is greater than or equal to 0, what will happen is you're going to get what you'd expect to get here, the Z to the minus n-naught, the one-sided Z transform of that right-sided sequence, which makes sense. But then you'll get, because you're moving things into the view of the Z transform, it'll be moving in the terms that were on the left-hand side will move in to the right-hand side, sort of as initial conditions, and that's exactly what we want to have happen. So that's the major difference there, and the definition starts in here in the time shift property, but sort of the punchline is this, which is the one-sided Z transform. We already talked about the theorem, but we'll have this those values that were sitting just to the left of n is equal to 0 will slide over and will be present. And those, like I said, allow us to solve for the initial conditions. So in a causal LCCDE, we had this from the very beginning, where we had linear combination of n plus 1 past outputs and n plus 1 past inputs are equivalent to each other, and that's what the LCCDE does. And then you can rearrange it if you want to and have the output in terms of the inputs in the past outputs. But if you apply the delay theorem to these terms in the sum where you have y of n minus k and x of n minus r, this is where things get a little bit messy. So this is where I'm just going to jump to the summary right here. And this actually is really cool the way it works out. It says when you have a one-sided z transform and you want to get y of z, like the convolution theorem would say x of z convolved to the impulse response, it'll be x of z times h of z. This is the ordinary h of z for a rational system, and it gets us y of z. So if there's zero initial conditions, this is what the convolution theorem says. It'll be x of z times, this is h of z. But when you have the one-sided z transform, because of the delay theorem, these two pieces here end up being the initial conditions, the values for x less than n is equal to 0 and y less than n is equal to 0. And then they carry through with the denominator from the h of z. And it's just the way the mapping works. The initial conditions get filtered by the all the poles on both the input and the past values. So that blue box equation just explains how the initial conditions work in. So it's really, I guess I'd say wonderful in the sense that it works just like it does in the Laplace domain. It's just the initial conditions are embedded in here if you need to worry about them. Most of the time we don't have initial states, so this is the same. This piece and that piece are the same for the two-sided z transform, but when you go to the one-sided, then these two terms get added in to represent the non-zero initial conditions. And I'm going to show like one example or two examples. And like I said, the exact mathematics is not super important. What is super important to me is to know that it carries over, because I feel like electrical engineering spends so much time with circuits in the very beginning, and then you learn about Laplace transforms and differential equations, and then you learn how nice that all works out when you can solve it with a Laplace transform, right? I made you look at classical solution of the difference equation, but you know, for my grading of two different papers, one person did a classical solution, the other one just did it all in the Fourier domain. And then after chapter 3, you do it in the Z domain. And in circuit theory, I think you solved, I remember when I was in circuit theory, we solved the differential equations. I remember the professor saying integral differential equations. So they had integrals and differentials, derivatives, depending upon whether it was inductors or capacitors, right? Because you have the integral differential relationships for those elements. And I just remember that as being kind of nasty, right? Laplace transform just made it manageable, very manageable. And for me, when I taught my circuits class, which Lake was talking to me about at the beginning of class, non-majors, I just gave them LT Spice, nurses, mathematicians, other people that wanted to learn how to do electronics without all the details that EEs go through. I practiced drawing schematics out, and then they had breadboards. They handled analog discovery, electronics kit they bought. They could make all that stuff work because LT Spice is not very hard to learn how to work. There's a lot of special features in it, but the core basics, they could do it really well. And I think in analog circuits, they would go that route. And I don't know, knowing that you're going to work for analog devices, I like analog stuff too. I liked it probably before I liked DSP. I like DSP better because I like playing on the computer. But if you like playing on the computer with your analog stuff, you can do that with Spice, and you can model other things in that way. If you're an IC designer, then you've got to implement it in chip form. So this example, though, takes a problem that we looked at a long time ago. Look at the clock. I think I'm really fast on this. It just says we have y of n is equal a y of n minus 1 plus x of n. And we know that the impulse response of that system is a to the n u of n. We learned that a long time ago, but remember also we did this recursively, and when we did it recursively, we could incorporate the initial condition, y of minus 1 equals c. And if you now formally go to what's in the blue box here, you would say, I will take what's at the top of the page, and I will z-transform the left-hand side, and then I will take x of z times the ratio. I mean, I did it term by term in here, but it works out, I think, the same way. I just did the one-sided z-transform of everything right here, and then I took into account when I z-transform this, because of the one-sample delay, I get the y of minus 1 with the a out in front of both of them, and then the x of z stands alone, and then solve for y of z, and then the y of minus 1 initial condition just pops out of that in the math. And there it is. Y of minus 1 is c, initial condition, and then you just have to inverse z-transform that using partial fraction expansions, term by term. And the signal function, .L filter, lets you incorporate initial conditions in an argument that's an optional argument out over here called zero initial conditions. So you can just put it right in there, and it will carry it forward. In the first problem of the project, you're going to do the same thing, and in this case, I just delayed a step to turn on at 5, but I put initial condition in so that it's starting to decay off from 0, and then the input turns on then, just as an exercise to go through it and see how it plays out. In my package that I wrote from January up until this summer for Maxima, I actually wrote my filter function over here so that you can incorporate the non-zero initial conditions right inside this argument, and then this would be the past values of the output and past values of the input. But for a first order difference equation, this stays empty because there is none, but there is one past value. And you actually develop code in Python very similar to this code for your project. I'm making you write it in Python. I wrote it in Maxima, and I decided, okay, it doesn't ruin your ability to do it for a project in here. It just teaches you about coding is what it really does. But here I did something pretty cool with the symbolic tool. I just put in constant C and just looked at what's going on when it first starts outputting, and you can see how the numbers get smaller and smaller. Mathematica and Maxima are pedantic about ratios of integers, so they get really big, and the screen, if you let it take off, it just fills it up with all kinds of symbolic stuff, which makes your head spin, but it is inside of there. If I just put it back to what I originally had it at, though, I'm not going to run it since I'm running out of time, I get, with no initial conditions, I get just the exact same stem output that I get from Python. You see the initial condition starts bleeding off the system like a capacitor discharging. Once you've started the system up at t is equal to 0, capacitor is discharging, and then the input arrives at 5, and it starts charging up the output because the input has got a step function driving it. You could pick, all kinds of different scenarios, but most every systems, like DSP systems I've been working with on this project at ARCA, there's states. Sometimes states are not always 0. You have to set them somewhere, especially if it's a control application. Or you've learned something from a certain interval of time, and then you engage some other algorithms later, and then you have states that are calculated initially. I always think of the control system example, though, where you might position something, or I guess in a cruise control for a car, what do you do when you turn the cruise control on? The car is running at 70 miles an hour. It doesn't start with the engine, with the car velocity at 0. That would be hideous for the passengers. But it starts with it already at that steady value, and then it continues to then engage the algorithm, which is sensing velocity and applying more gas to the pedal, effectively. Does that make sense? I don't teach control systems, but I did write that in my Signals and Systems for Dummies book. I actually took the engine example because there's wind resistance in a car, and I studied that. I read about it on the internet, and then I wrote it up. So we know that to be true. And we also know when you go up a hill, there's more gravity pulling against the car, so the engine has to work harder. And that is in the control systems for that too. Okay. I'm going to just take a look at a couple of the problems. I have like a minute to look at them, so don't have very much time. First one is problem number 3, or no, number 2. So A is very straightforward, but C has this triangle function in it. So very similar to the first homework assignment, but just the way it happens to work out. So this actually is part B. So you actually have to work part B to get part C, this problem. But XB is just a rectangular pulse that contains n samples, and that's already been worked in the notes. We did that rectangular shape, right? To get the triangle, you can just convolve the two rectangles, so that's how you can end up getting the Z transform of this sequence, because you just get the Z transform of this, and then over here, you just take the first one times the second one. And this is correct because when you convolve two sequences, the starting point is the sum of the starting points, so this starts at 0, and the ending point is the sum of the two ending points, so n minus 2 is the last non-zero value over here. So that will be the triangle, and
Shouldn't it be 2n minus 2?
yeah, it's 2n minus 2, I guess. I don't know. I'm looking at my drawing. Yeah, 2n minus 2. So what I want you to very carefully consider when you draw your pole and zero plots, you will get this without a problem, but you're going to have repeated roots, so make sure you make note of that. The fact that you're going to have repeated roots, because this has zeros spaced around. Then it'll be a product in the Z domain. So you'll have roots that are doubled up. So make sure to make note of that stuff. And I took an example to make sure my math was working right in Python, and I used Z-plane. So I want you to have Z-plane working so you can have it draw pictures for you. You will see it do its thing. Okay, so next problem that I think, I realize I'm taking a little bit longer. I'm not going to be able to cover everything, and I know you can't absorb everything all at once either. You got to engage your brain in it. Sorry, it doesn't get any better. I mean, you get older and then your brain starts to fade out on you probably too, but the only way I really get going on something good is after you just immerse yourself into it, and then you get really focused on it. So this is the one that has 3 terms in it, so this is just tedious. So I'm kind of drilling on this because I've seen this worked in the past, and they tell you it's stable. So if it's stable, what do you know about this? It's got to pull at -1/2. It's got to pull at 2 and at 3. Well, it's got repeated pulls there, but so what do you know if it's stable? The region of convergence has to include the unit circle. So the region of convergence is interior, exterior, or annular? It's going to be annular, right? Because if it's going to include the unit circle and you've got poles outside and poles inside, it has to be an annular shaped region. So make sure when you inversely transform, you get left and right sided sequence components in there. That's must happen. And that will throw in minus signs because of the way the inverse transform pair works. In terms of actually doing it, you can do the exact technique I mentioned. You have to expand this into 2 terms, but one of the 2 you can get immediately from the residue formula. And then these 2 are simple poles, so you would use that technique that I used in class, except you add in 1 more term, right? Pick a location, you'll probably pick Z is equal to 0. Just looking at it, that works, right? Because it doesn't blow up at Z is equal to 0. And then you'll be able to get all the coefficients and check them using residue Z on this one. Last thing, last but not least, 2 problems actually. Problem 7 has got feedback loops in it. How is everybody on feedback? Block diagrams and feedback systems. You're in it right now? Okay.
I'm not in antenna engineering.
Well, I mean,
So it's called superposition in a linear feedback, or in block diagrams, I mean. So what you have to do when you have a feedback system and you know linearity applies, if you want to find W of z, so what you want to be able to do is switch this to the z domain, because then it's just algebraic. There's nothing that's going to get you twisted up. So switch everything to the z domain notation by z transforming all the quantities, and then you have to think you're going to have something like this. And I may have these wrong, but I think that's right. Yeah. So H2 of Z and H1 of Z. And the way you work the block diagram problem is you use superposition. So start the problem by, say, turning off E of Z. Don't let it be running, and just apply this, and then work your way over to W. So call it W1. So you can say that this is like that. So W1 of Z you get by turning off E and just applying X, and W2 you get by turning off X and turning on E. So how do you actually do either of these two block diagram things? This is the way I like to do it. I mean, there's different standard formulas and things for working the block diagrams, Mason's gain formulas and things like that. I think control systems people used to talk about. I really don't know what they do anymore. But the way I would do it, I would say, I'm just writing this generically, W of Z is equal to what? I'm standing right here. How do I get that? That's going to be, I'm going to set E of n equal to 0. So when I do that, what do I have sitting right here? I'm just going to write notes on here so you can make sense out of it. That's going to be x of n minus what? W of n. And then that goes through h of z and comes through the output. So I can sit over here and I can say W of z is going to be x of z minus Does that make sense?
That would be like W1.
Yeah, this would be W1, but I can just write that, right, from algebra? So I can just move the WZ terms to the left-hand side, and then I'll have some expression which will factor out, which will be x of z times some h1 of z. And when I do the opposite setup, I'll have the same thing going on, and that'll be my W2. I'll turn off the input and just turn on the other input, E. This gets analyzed in more detail in a later chapter, so you'll understand what this is all about when we eventually get there, but it's just an exercise right now. So just keep it simple and then just follow the problem all the way through. So you'll build it up from pieces, and then they ask you some questions. There's one other thing that I realize I'm way over. I just want to say problem 346 is a tricky little thing. This is problem 8. I think my computer is getting tired because the video is getting really long, so it's very sluggish. I draw and then it takes a long time for it to do anything. 346 though, it's very, you have to very much be a detective in this problem. It gives you an input, it's got a two-sided input, then it says find the z transform of x of z. So how would you even find x of z? Well, just remember that y of z times h of z, so you can go x of z so you can write all that stuff down, but then you have to think what is really going on here, and you have to think about regions of convergence. So you have to study what's going on with the regions of convergence all the way along. Just keep kind of focusing on that. We're starting off with a two-sided sequence, and then what is x of z going to be? Just have to think about it. Unless you have a pole zero cancellation, you don't have, you know, the annular region will stay there, but you might have a pole zero cancellation. So just kind of just keep modeling your way along by, you know, keeping your focus going is what I'd recommend. It's interesting. It just takes you on a trip, pretty much. It's a problem. It's like a story problem. It just keeps taking another piece, and you just keeping the basics. I think that's all I want to say for right now. I'm tired, but talk to me on Slack, though. What's your question?
Yeah, so for problem 7, feedback, why can't you just do it in, and maybe I should ask my feedback teacher, why can't you just do it in one equation with, like, putting the e of z, adding that in?
Oh, back over here?
Yeah.
You can if you feel comfortable with that, but I'm saying you can think of turning one off because superposition has to hold if it's a linear system. So,
Okay, so that it would come
you have Dr. Plett or Dr. Trimboli?
flat.
Okay. Those guys are both really good, so they're my closest friends, I guess I would say, because we share a bond of signals and systems together. Yeah, you can do it that way too. This is a very simple system, but when we study this later on, you should be intrigued by it. It's a model of an electronic part. I'm not going to explain it right now, but we'll get there. It gets talked about more in the next chapter, actually. So let's look at your Z-plane. I'll sit down and drive your computer. I'm going to stop my video, though, and let it settle.